a lot of the operations that you can do for matrices, like addition, scalar multiplication, matrix multiplication, have parallels in ordinary arithmetic of real numbers. You have the same kind of operations on real numbers as you do on matrices. And a lot of the properties of real number arithmetic also hold for matrices, as we're going to see in the next video. But there's one operation which is very special to matrices and which doesn't have a parallel in ordinary real or complex numbers. And that is the transpose. So here's the definition of a matrix transpose. You begin with a n by n matrix A, like this, and then the transpose of A, which we write like this with a superscript capital T, is an n by m matrix, so the opposite way round to A, whose ij entry is the ji entry of A. So let's see what's going on with this definition. Let's say we began by taking a column vector. So we might take x to be the column vector 1, 2, 3. Now this is a 3 by 1 column vector, so x transpose will be a 1 by 3 row vector. And let's work out what the entries of x transpose would be. So the 1, 1 entry of x transpose will be the 1, 1 entry of x. So that will be 1. And the 1, 2 entry of x transpose will be the 2, 1 entry of x, which is this, the one in row 2 and column 1. So we should put a 2 here and of course a 3 here as well. Okay, let's try a slightly different example. Let's have A to be the matrix 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix, so its transpose, a transpose written like this, would be 3 by 2. It would have 3 rows and 2 columns. And again, the 1, 1 entry of A transpose would be the 1, 1 entry of A. And the 1, 2 entry of A transpose, so the thing that goes here, will be the 2, 1 entry of A, which is the thing here. So we would have a 4 just here. And similarly, we would have a 2 here, and a 5 here, and a 3 here, and a 6 here. Okay, so you will notice from looking at this something which is generally true, which is that the rows of A correspond to the columns of A transpose. And of course, the columns of A become the rows of A transpose. So if we look at the example we've just done, the first column of A 1, 4 became the first row of A transpose, and the first row of A 1, 2, 3 became the first column 1, 2, 3 of A transpose. Similarly, another thing which you would notice from this example, but which is true in general, is if you took A transpose transpose, then of course you get just A again. Alright, let's try one more example. So we'll take a square example. Let's take A to be the matrix 1, 2, 2, 1, like this. Then A transpose is equal to 1, 2, 2, 1 again. So in this case, A is equal to A transpose. And there is a special word for matrices which are equal to their own transpose. So we say A is symmetric if and only if A is equal to its transpose. So symmetric matrices have to be square because A is m by n and A transpose is n by m, so if they're to be equal, n must be equal to m. Now we won't actually use the transpose, we won't actually use symmetric matrices very much in Math 5, but it's a term which is standard and which you'll come across elsewhere. Okay, let's look at a special case of the transpose, because there is a useful special case which you will quite possibly have seen before, which is the relationship between a dot product, I'll explain what that is in a second, and the transpose. So if you have a column vector, let's say x is going to be 1, 2, 3, and you look at another column vector y, let's say 4, 5, 6, then I can work out x transpose y. And if you think about the size of this, well, X transpose is going to be 1 by 3, and Y is going to be 3 by 1, so their product will be 1, 1, 1. 1 by 1. It will be a 1 by 1 matrix, and we usually identify those things with numbers. So here, if you work out X transpose times Y, that's 1, 2, 3, matrix multiplied into 4, 5, 6, and the answer here is going to be 1 times 4 plus 2 times 5 plus 3 times 6. Okay, a number. So normally we will identify 1 by 1 matrices with numbers. And this is what people talk about when they talk about a dot product. So a dot product between two vectors is a way of getting a number out of two column vectors of the same height. And this is the way that it's done. We can even use dot products, and so transposes, from a geometric point of view. These have a geometric meaning, because if we take the example vector that we've just looked at and worked out X transpose times X this time, if you think what you would get here when you do X transpose X, you would get 1 squared plus 2 squared plus 3 squared. So that thing has a geometric meaning. That is the square of the length of the vector X. So if you want to think about this in 2 dimensions, you can draw yourself a picture to see what's going on there. Let's draw some coordinate axes like this. And then if you had a vector which was here, so the vector, if we draw this line from 0 to my point here, which is, let's say, the vector 2, 3, then the square of the length of that line by Pythagoras' theorem is 2 squared plus 3 squared. That's the length of this diagonal line here. So the length of the line from the origin to the point represented by this vector. So for real vectors, at least, there is geometric meaning for these dot products. So the matrix multiplication X transpose times X gives you the square of the length of X. And in fact, there's a general geometric interpretation for the dot product of two vectors. Now, we're not actually going to use this in Math 5, so I won't go into any detail, but I think I really just would like to mention that there is a mathematical expression, a geometric expression for the meaning of X transpose Y, this dot product, and the answer is that it is the length of X, so by that I mean the square root of X transpose X, times the length of Y times cosine theta, where theta is the angle between X and Y. Alright, so by this symbol here, I mean the length of the vector X. And there's a special term for vectors, pairs of vectors, where this angle is a right angle or minus a right angle, and that is, we call those vectors orthogonal. So it's equivalent to say that two vectors are orthogonal if their dot product is 0, because that will be the condition for this angle cos theta to be 0.